So yeah, I think there is an audio issue. So I'll start again. So welcome to class 8 of stochastic control and communication. So in the last class, we saw the similarity between stochastic control problem, general stochastic control problem, and the shortest path problem. So we thought that we could, since both of them have the same formulation of you taking a decision, and then because of the decision that you have taken, you incur a cost. The same thing you see in the shortest path problem. And the cost is additive. So at each step that you take the cost that you incur for taking the step is added up. The same is with stochastic control and shortest path problem. And what you want to do is you want to minimize the cost that you incur through to go from A to B in a finite setting, which is the same as the finite horizon stochastic control problem. But just the differences in stochastic control problems, your path trajectory is random, whereas in the shortest path problem, they are not random. So yeah, yeah. So based on this, we saw the principle of optimality, where let pi star this be your optimal policy in the space of Markov decision policies be the optimal policy. Then if you have the assumption that if you use this policy, then the probability of you ending up at state xi at time I is non-zero, right? If this assumption is true, that means if you use this policy with some non-zero probability, you are bound to end up at state xi, right? Then if we want to find the optimal solution for the sub-problem, that is if you start at xi and you want to reach xn, that is the cost function that you want to minimize now is the terminal cost plus the stage-wise cost, but now starting from I. Then your optimal policy is basically a truncated version of the original policy. So if you know that this is your optimal policy, then for the sub problem of starting from the middle, your optimal policy will be the truncated version of this optimal policy. If this is not true, right, then this will not be your optimal policy. Then you can from state I, you can generate a new policy where from state I you have this new vector of functions mu I to mu n minus 1, which optimizes this and which will give you a lesser cost than this optimal policy. So that is intuitively seen here. So this is what your principle of optimality suggests, and uh, based on this principle of optimality, we have come up with the dynamic programming algorithm, where you have the algorithm. I've just written on the algorithm is you find the J and cost functions for each and every time in a recursive way from the back. So you do it for mm, first you do it for the end state. You just put them as terminal cost, and then you calculate Jn minus 1 using Jn as a recursion one step, and then you do it for each stepwise, and then you come to 0, and then you say that okay, I gather all the UKs that I have found by solving this equation, and I put them as a function mu k star xk, and if this UK minimizes this, then I have my policy, and this policy is optimal. So we gave a proof for this yesterday, but the proof was um, you have a policy pi and you have a truncated policy pi k. Similarly, we defined jk star xk, which is your optimal cost of the truncated problem, which is of n minus k stages. Right. And mathematically, this was given as jk star xk equal to minimize pi k such that your expectation over gn xn plus summation I equal to k to n minus 1 gi xi mu y xi wi. This is for all xk. This is your minimized. So and what we showed is and we took that Jn star xk is equal to gn xn. And what we showed is jk star xk is jkxk. And now this jkxk is basically from the dynamic programming algorithm that we have found. And this jk star is the optimal subproblem solution. If both of them are the same, then what it says is, if you follow this dynamic programming algorithm, the policies that you get is the same as you optimizing all your subproblems. Okay, so this was your dynamic programming problem. We showed this by induction. So we showed this using induction. Next, we saw an example for inventory control using dynamic programming. Okay, so just let me quickly revisit the inventory control problem where you had min UK greater than or equal to 0, so that expectation of Rxn plus summation k equal to 0 to n minus 1 Rxk plus Cuk. So where Rxk is your storage cost and C is your per unit inventory cost. And if you have ordered UK amount of inventory, UK is the amount of inventory that you've ordered. Then C into UK is the total cost that you pay to buy your inventory. RKXK is the storage cost. So after each time you have, because you have to store XK unit after each decision epoch. So you are basically paying cost of RKXK for storing, and this is your terminal cost. Okay, so first we'll do the general dynamic programming for inventory control. So where we'll have gnxn equal to gnxn, gkxk. I'm writing the dynamic programming problem once again. uk mu k, expectation of gkxk uk wk plus jk plus 1 your system dynamic fk xk uk wk, and you do this till you come to j star x0, which is j0x. Okay, so here this is your general dynamic programming algorithm. Okay. Now for the inventory control, using dynamic programming, we get, so now we are doing it for k equal to n minus 1 step. So first we do it. Okay, so the first step is you do it for k equal to n. So the last step, so that is jn xn. Jn xn equal to rxn. Okay, and Now we do it for k equal to n minus 1. So we have j n minus 1 x n minus 1 equal to minimize u n minus 1 greater than or equal to 0, because this is because you can order positive amounts of inventory. And expectation of CUN minus 1 plus RXN minus 1 plus RXN. Right. From here, the observations that you make is this is not random, because this is a function of xn minus 1 and you know xn minus 1 and un minus 1 is the decision that you're taking, so it's not random. This is not random, but there is randomness here because of dynamics, because xn equal to function of xn minus 1 un minus 1 wn, and this wn minus 1 is random. And because of this randomness, you are getting this expectation. So your expectation is basically over this randomness, right? So basically, you can take these two out of the expectation, and then you get min un minus 1 greater than or equal to 0, cun minus 1 plus r xn minus 1 plus expectation of r xn minus 1 plus un minus 1 minus wn. We'll leave it here for now. Today only, in the next, while doing the example, I'll try to come up with a cost function and also some variables that or some statistical assumptions for wn minus 1 and also some constraints on xn minus 1 plus un minus 1, and we try to solve so that we get a closed form solution of optimal policy. Okay. So before that, I just want to do it for jn minus 2 xn minus 2. So this will be minimum un minus 1 greater than or equal to 0. So that expectation of cun minus 2 plus r xn minus 2 plus jn minus 1 xn minus 1. So what this means is you are minimizing your expected cost in time period n minus 2. Now, this expected cost in time period n minus 2 is basically this. This is your expected cost in time period n minus 2 plus you're also minimizing expected cost in n minus 1, assuming the optimal policy is chosen in n minus 1 stage. So basically, this optimal policy is chosen is basically this is the optimal policy that is chosen because you already know what the optimal policy is, right? So this is what you're doing. I'll not okay. I'll maybe elaborate for just this one. So you have min un minus 1 greater than or equal to 0, un minus c into un minus 1 plus r xn minus 2 plus expectation of jn minus 2 at xn minus 2 plus un minus 2 plus wn minus 2. Okay. Okay, so today I'll take an example problem in the inventory control. So this was a general inventory control problem, but now I'll take an example problem and we'll solve it from the beginning to the end so that you get to understand. So before that, we have to make some assumptions. Now those assumptions are your WK can only take integer values, that is 0, 1, 2, so positive integer values. Your UK can also take only positive integer values, that is 0, 1. And the dynamics that we defined last time was xk plus 1 is max of 0 comma xk plus uk minus wk, where xk is the amount of inventory you had at time k, and uk is the amount of inventory you ordered, and wk is the demand that you get in eighth slot. Now, this wk is a random, you don't know the value of wk, right? Okay. Um, and we have some constraints saying that xk plus uk is less than or equal to 2 and uk is greater than or equal to 0. Using these two, you get the constraint that uk is between 0 and 2 minus xk. Okay. Now, what does this constraint mean is you can store only two amount of inventory with you. You can't store more than that. So if you have one amount of inventory, you can either order nothing or you can order one. You can't order two or more than one because you don't have that much amount of storage in your space, right? Okay. So next we'll define the holding cost or storage cost. So because you're ordering something, you'll pay some money to store that thing, right? And that cost would increase as the amount of storage things you have to store increases. So basically, it will be xk plus uk minus wk whole square, where this is your xk plus 1, right? Plus max of both, but this is your xk plus 1. This is your holding cost or storage cost. And if you have not met the uh, demand because you have less amount of storage, then also you'll get pay a penalty. That penalty is just not fulfilling demand. And that will also be satisfied by this. And next you have your per unit cost to buy inventory. So the per unit cost of buying inventory is 1. So basically, if you buy UK amount of inventory, then your um, cost is UK. The terminal cost, I'll put terminal cost as 0 for all states. For any state you go into, it will be 0 always. So don't worry about that. Terminal cost is 0. So you don't pay any cost for terminal cost. Now we have to give some statistics of noise, right? And here your noise is WC. This is your noise. This is your noise. So I'll add on statistics of your noise. Is probability of WK equal to 0 is basically 0.1. Probability of WK equal to 1 is 0.7. And probability of WK equal to 2 is 0. Right. If probability of WK equal to 3 was non-zero, then there would be no point because you have a constraint that you can't store more than 2. So basically at most your demand would come, that would be 2. Right. So uh, it's no point in getting a demand 3 because you don't have that much and you'll always keep paying a penalty. So this constraint that you can only store 2 is known with the customers. So customers, either there'll be no customers that ask for inventory, there'll be either one customer who asks for inventory, there'll be other two customers who ask. Okay? And the probability that you have demand 0 is 0.1 and the probability that you have demand 1 is 0.7, the probability that you have demand 2 is 0.2. Right? We will solve this problem for n equal to 3. So basically think of it as 3 days. You're doing an inventory control for 3 days. Okay, so first we'll do it for n equal to k equal to 3. So k equal to 3, j3xk is equal to 0 for all x3. x3. Okay. Next, we'll do it for k equal to 2. Right? K equal to 2, your states, they can take either 0, 1, or 2. Okay. So first we'll do it for x2 equal to 0. So basically you're writing j2 0. And as per the random programming, this is minimize 0 less than uk less than 2 expectation of u2. This is u2 plus x2 plus u2 minus w2 whole square plus j3, not 0, j3 x3. But since j3 x3 is 0 for any x3, so you don't need to worry about this for now. Okay. And since u2 can only take integer values, since u2 can only take integer values, this becomes minimizing over u2 belongs to set of 0, 1, 2. Right? Expectation of u2 plus x2 is 0 here. So you have u2 minus w2 whole square. Okay. Now what you do is you evaluate this function. You evaluate this function at all three values. U equal to 0, u2 equal to 1, and u2 equal to 2. So it basically becomes min of evaluate this expectation at 0. Mm, hmm. So expectation W2 square, comma, expectation 1 plus 1 minus W square, expectation 2 plus 2 minus W2 square. Okay, we'll first calculate this. This is basically 0 into zero point 0.1 plus 1 into 0.7 plus 4 into 0.2. That will give you 0.1 plus 0.7 plus 0.8, 1.6. Okay, next we'll calculate this. So this is 1 plus 1 into 0.1 plus 1 into 0.7 plus 1 plus 1 into zero point 0.2. This will be 0 0.2, 0 0.7, 0 0.9, 0 0.9 plus 0.4, 0.13, 1.3. Okay, and next we are calculating this value. This value would be 2 plus 4, 8 into 0.1 plus um, 2 plus 1, 3 into 0.7 plus 2 plus 2 into zero point 0.2. So we have 2.1 plus 0.8, 2.9 and zero point 0.4 is 3.3. So basically you have min over 1.6, 1.3, 3.3, and which is 1.3. So basically you get a cost, the optimal cost for x2 is 0.3. But when do you get 0.3 is when you choose u2 equal to 1. So your u2 star is 1. So what you get is j2 star 0 is 1.3, and that means that your optimal strategy, if you end up at 0 when you are in the second step, is to take u2, is to take yeah, this is 1 when u2 is 1. This is u2 optimal. This is u2 star. Okay, next we have to do it similarly for if x2 is 1, because x2 can also take 1. Okay, so suppose x2 is equal to 1, then j21 equal to, now since x2 is 1 and you have that constraint that u2 is less than x2 minus 1, x2 minus 2 minus x2, this constraint 2 minus x2. So u2 can only take values 0 and 1. So u2 belongs to 0 and 1, and you have expectation u2 plus 1 plus u2 minus w2 whole square. Here there is a 1 because your x2 is 1. Okay, similarly, this becomes minimum over, now you calculate it for 0, you get 1 minus w2 whole square. So expectation of 1 minus W2 whole square and expectation over 1 plus W2 whole square. Okay, these two have to come. Yeah, obviously this will be less, but we'll have to see. So this first one would be 1 into 0.1 plus 0 into 0.7 plus 1 minus 2, 1. 1 into zero point 0.2, which is basically 0.3, and this would be 1 into zero point 0.1 plus 2 into 0.7 is already greater than 0.3. Therefore, J2 star 1 is 0.3 and mu1, mu2 1 star is basically 0. You get it when you apply 0 as your UK. So now you see you're describing these optimal policies for each state. So your optimal policy is, so now we have seen that mu 2 star of xk, you are defining it. With this function, you get it as 1 if xk equal to 0, 0 if xk equal to 1, the x2 equal to 0 if x2 equal to 1, and similarly now you have x2 equal to 2, x2 equal to 2. There's only one action that you can take because you can at least store 2. You can't store more than 2. So your mu2 star is basically 0. You don't order anything. But then it's important to calculate the optimal cost that you get when you're at 2. Because what happens is you need to use this cost in the next iteration here. Yeah, here you need to use the optimal cost if you end up at that state. So you don't know at what state you'll end up here because of the randomness here. So you need to calculate the optimal cost for all. Even if you know the optimal action, you need to calculate the optimal costs. This will be important in the next steps that has to come. Okay. Yeah, so this this becomes 0.1 into 4 plus 0.7 into 1 plus 0.2 into 0. So basically 0.7 plus zero point 0.4, which is 1.1. So your J2 star 2 is 1.1. So we have done with this K2 equal to 0. Now we have to do it for K equal to 1. So I'll let down K equal to 1. At K equal to 1, xk can again take 0, 1, 2, any of these three values. So first we'll do it for x1 equal to 0. So we want J1 of 0, right? This is minimize U1 over 0, 1, 2. Because if your x1 is 0, you can take any action 0, 1, 2. And we want to minimize expectation of U1 plus x1 minus W1 whole square plus J2. This is x2, but x2 written as max x1 plus u1 minus w1. Okay. Now x1 is 0, so this is 0. So this is max u1 minus w1. And we are minimizing u1 equal to 0, 1, 2. Expectation over u1 plus u1 minus w1 whole square plus j2 max 0 comma u1 minus w1. So first we'll do it for u1 equal to 0. So u1 equal to 0, you get expectation w1 square plus j2 of 0. This will be 0 always because u1 minus w1 will be minus w1 and 0 will always be greater. So now we had j2 0 star was 1.3. So this will become 1.3. Right. So this is expectation of w1 square plus 1.3. And expectation of w1 square is 0.1 into 1, 0.1 into 0, 0.7 into 1 plus 0.2 into 4. So basically 8, 1.5 plus 1.3, which is 2.8. Now we'll do it for u2 equal to 1. So then this will become expectation of 1 plus 1 minus w1 square plus j2 into max of 0 comma 1 minus w. Okay, so this is basically 0.1 into 2 plus j2 1 plus 0.7 into, because now here if w1 is 0, this will be 1, so max will be 1 out of both, out of 0 and 1 minus w1. So next 0.7 into 0.7, w1 is 1, so this will be 1 plus j2 0 plus 0.2 into 2 plus j2 0. So this is 0.1 into 2 plus j2 1. The optimal j2 1 is 0.3. 0.3 plus 0.7 into 1 plus 1.3 plus 0.2 into 2 plus 1.3. So this is 2.3 into 0.1, 0.23 plus 2.3 into 0.7, 2.3 into 0.7. 2.3 into 0.2, 0.66. 1.051 something. Similarly, if you calculate in the same way u1 equal to 2, you'll get 3.68. So mu 2 star 0 is basically 1. Yeah, we are doing it for state 0. Yep. And J10 equal to 1.051. Okay, in this manner, you have to continue, keep on calculating for all states. So now you have to calculate for J11 and J12, right? Similarly, after you have found these, you have to calculate for J00, J01. Oh, I think you can make that assumption that at the first state you don't have any inventory. So you just calculate for J00. You can't take any other states in the initial state, and then you're done. So you calculate these three, and then what you'll get is you'll get the pi star would be mu 0 star, mu 1 star, mu 2 star. Right. And this mu 2 star is basically a mapping from x2 to u2. So you give any x2, you'll give you a plan saying that okay, if you are at this x2, then you take this action. If you are at some other x2, then take this action. Because which x2 you'll be at will be random. So you don't know a priori which x2 will be. So you plan for all possible cases of at what x2 you'll be, you'll take that decision. Right. So this is an example for dynamic programming. So tomorrow, in tomorrow's class, we'll see something on something known as optimal stopping problem. This is also a decision making problem, a different type of decision making problem, and we'll model it as an MDP and then try to solve this MDP using. We'll try to solve the optimal stopping problem, you modeling it as an MDP and try to come up with an optimal policy there. Recording.